Knowing the weather before it happens is pretty important these days. We check before work, before school, before deciding if it's a hoodie or t-shirt kind of day. But how do we actually know what the weather is going to be days before it happens? How can someone tell you it'll rain in 3 days? Or that Saturday will be partly cloudy with a chance of wind? Let's go right back to the start. Before we had satellites and supercomputers, predicting the weather was more of an art than a science. In the 19th century, we began using instruments like barometers and thermometers to measure air pressure and temperature. When pressure drops, it often signals bad weather on the way. When temperatures change, it indicates shifting weather fronts and the likelihood of things like frost, heat waves, or storms. By the early 20th century, we could track pressure systems and fronts across maps, but it was still mostly done by hand, and forecasts were pretty vague. Now we have tools the early meteorologists could only dream of. Let's break these down. The first thing needed to predict the weather is data. Lots and lots of data. Every day, thousands of weather stations, satellites, ocean buoys, and aircrafts all over the world collect information about the atmosphere. They measure temperature, wind speed, humidity, air pressure, cloud cover, everything. This data gives us a snapshot of what Earth's atmosphere looks like right now. That could mean a jet stream surging across the Atlantic, a low-pressure system spinning over Europe, or a warm front moving up from the tropics. These patterns show us how energy and moisture are flowing through the atmosphere, and they set the stage for what happens next. And this is the starting point for all weather predictions. Once we have the data, we feed it into something called a weather model, which is basically a massive simulation of the entire planet's atmosphere. What this is doing is dividing the Earth into a 3D grid full of cells and calculating what's going to happen to each one. It uses physics equations to figure out how air flows between these grid cells, how heat is transferred, how moisture condenses into clouds, and where all of it moves next. For example, if warm air is rising in one cell and cold air is pushing in from the side, the model calculates how those forces interact. Will it form a storm or just shift the wind? Each grid cell is constantly updating based on the grid cells near it, like a chain reaction of atmospheric changes. And they do this for every hour across thousands of vertical layers over the whole globe. That's why we use supercomputers. These machines are capable of doing trillions of calculations per second, because every point in the atmosphere affects every other point, and it all needs to be updated constantly. So when your weather app says it'll rain at 2 p.m. in your town, that's because the model saw conditions that formed rain in that area. It saw things like rising humidity, falling pressure, a cold front pushing in from the west, and the computer recognizes it and calculates that it means rain. But the atmosphere is chaotic. One tiny measurement change can cause the entire forecast to shift. That's why predictions get less accurate the further in the future you look. To deal with this, meteorologists run hundreds of models, each with slightly different starting data. This is called an ensemble forecast. If most of these models are predicting the same weather, that builds confidence, so it's safe to assume that will be the weather. If they don't agree, it means uncertainty. So a 60% chance of rain in your town means that 6 out of 10 simulations ended with rain in your area. And weather predictions are getting better. As we launch better satellites, build better models, and train AI to recognize patterns, forecasts are becoming more detailed, more local, and more accurate. They're still not perfect, though, let's be honest, but we are getting there.